In this lecture, we are going to extend our discussion about hypotheses and talk about what it means to actually test a hypothesis. We'll talk about a null hypothesis, and as this hilariously inappropriate meme suggests, we will also talk about the infamous p-value and how we can use probability to test a hypothesis. Quick recap from last lecture. We talked about the importance of falsifiability. Hypotheses must be falsifiable. Hypotheses should be simple and directional, and in the case of ecology, generally non-specific to the system. Predictions are logical statements that come from a hypothesis. We say, I hypothesize that, ... Given this hypothesis, I predict, ... We also talked about inductive versus deductive logic and how science is generally an inductive process. And then we talked about fishing, or the dangers of developing too many hypotheses. I want to start off with a quick observation. All right, this is something I saw on YouTube a while ago, and I'll share it with you now. Why did they do this? I hypothesize that territorial animals splash at humans when we approach their territory to warn of competitive superiority. Note that this is talking about territorial animals in general, not about gorillas. It's talking about a broad mechanism. Given this hypothesis, I predict that if I do an experiment with gorillas, I will find ... So I'm going to do some experiments. All right. From here in, we will refer to this as the alternative hypothesis. This is confusing, I know, because we talked about those fishing expeditions and how we can have multiple hypotheses. Any hypothesis that is not the null hypothesis, which I will introduce in a second, is called the alternative hypothesis. And you can have multiple alternative hypotheses. The null hypothesis is where we hypothesize that the activity we observe is due to random variation or measurement error. I want you to concentrate on random variation. The idea that everything that you see is due to randomness. There is no pattern. In this case, the null hypothesis is there is no mechanism or pattern for knowing when gorillas splash. Please note, the null hypothesis is not they do not splash at humans. After all, they did splash at humans. We saw it with our own very eyes. But the behavior that we observed is due to randomness, that there is no reason for this to occur. It's just due to randomness. It's frustrating, I know. Hold on to that frustration. Your mission in science, all of science, regardless of the field, your mission is to reject randomness. Reject the idea of randomness. That is what science is about. We reject the null hypothesis of randomness. If you do not find evidence to support your alternative hypothesis, it does not mean that your alternative hypothesis is wrong. After all, there is no wrong and right, truth, or fact. It only means that you did not find evidence to support that alternative hypothesis. Again, it does not mean that your alternative hypothesis is wrong. Suppose that you did an experiment. You all will do an experiment. Please remember, if you don't find evidence, it doesn't mean that your hypothesis is wrong. It just means you didn't find evidence to support it. This is a really important distinction, and you'll understand why in just a second. We fail to reject the null, but we never accept the null. We never accept the concept that everything is random. You never accept this. because all of science is built on the notion that the universe is not random, that we can understand patterns in the universe. We never accept the null hypothesis of randomness. We always just say, fail to reject the null. And we only say that we cannot find evidence to say that things are not random. I know that this is confusing, so please stop and go back if you need to. One thing that I'm going to use to drive this home was the flat Earth example from the previous lecture. In that example, the researcher with the telescope looking over the horizon hypothesized that the Earth is round. That was their hypothesis. The Earth is round. The null hypothesis was that there is no evidence for a round Earth. The null hypothesis was not that the Earth is not round. That's not what we make a hypothesis. The null hypothesis is simply that there is no evidence for a round Earth. He conducted an experiment that failed to reject the null, because remember, he saw the boat continuing on the horizon, and this didn't make any sense given his mechanism, given that the Earth should be round. He failed to reject the null. He failed to reject the idea that the Earth is not round. And consequently, he failed to accept the alternative. Responsibly, he did not conclude that the Earth is not round. Remember from this slide, we don't hypothesize that the null hypothesis is not that the Earth is not round. He did not make that conclusion. He did not conclude that the Earth is not round. He only concluded that he did not find evidence for a round Earth. Flat earthers use a failure to reject the null hypothesis as evidence that the alternative is wrong. This should raise serious red flags for you. Worse, they then suggest that this failure to reject the null is evidence for some other shape. In other words, flatness. Flat earthers rarely conduct experiments that actually test the hypothesis the Earth is flat. Rather, they generally use lack of evidence to support a round Earth as evidence of a flat Earth. This is some seriously flawed logic. One other point that I want to bring up is you cannot actually test a null hypothesis because a null hypothesis is not falsifiable. What do I mean by this? Well, we talked about falsifiability in the previous lecture, but now we're really going to apply it. Suppose I hypothesize that vaccines cause autism. This is a valid hypothesis. Certainly we can test it, and people have tried to test it. If I fail to find evidence that vaccines cause autism, this does not mean that the vaccines do not cause autism. Maybe go back and read that again. If I fail to find evidence that vaccines cause autism, this doesn't mean that the vaccines don't cause autism. To know that they do not cause autism, I would have to test every single human for autism at every point in time throughout all of history. That's not going to happen. It's frustrating, I get it, because we cannot say vaccines don't cause autism. But science is not in the business of finding absence of patterns. Science is only in the business of finding patterns. Why does this matter? Well, if you know anything about the anti-vaccination movement, scientists say, I cannot say with 100% certainty that vaccines do not cause autism. Scientists also say, I cannot say with 100% certainty anything. Anti-vaxxers say, oh, so they do cause autism. No, that's not what I said. I said, here's a bajillion studies that suggest that they do not cause autism. Yeah, it's frustrating. Getting back to our idea of the null hypothesis, let's develop another example and also talk again about the philosophy of hypothesis testing. Alligators apparently do the exact same thing as gorillas. So I hypothesize that alligators increase splashing behavior around competitors to avoid competition. Easy enough hypothesis. They splash their tail to avoid competition. Ideally, to test this hypothesis, I would put competing alligators next to my test alligator. But I don't know. I mean, that seems like a really dangerous thing to do, but I would then observe the response. I don't know, airlift. I don't know how you even pick up an alligator, but maybe airlift alligators somewhere. Realistically, I don't want to be eaten, and so I'm not going to pick up an alligator. So what am I going to do? Practically, I test my hypothesis by placing a stereo near my subject. I simply play back alligator noises to my test subject. All right, so I stand near this alligator close enough that it can hear my stereo, but far enough away that I can run like mad if it starts attacking me. Okay? I didn't do this experiment, but my friend in Costa Rica did it, and I was there when he did it, and I had to be his wingman, looking to make sure if alligators were ready to attack. I probably will never do that again. Suppose that they do not splash when you play the stereo competing alligator noises. In that case, we have only failed to find evidence to support your mechanism. Again, and this should not be new to you, it does not mean that your mechanism is wrong. There is no wrong and right. It just means that we didn't find evidence to support your mechanism. One of the reasons why you didn't find evidence to support your mechanism is because alligators know the damn difference between a stereo and an alligator. I should say, and an alligator. Maybe they need a visual as well as audio. Maybe you just didn't do the experiment, or maybe you had bad assumptions when doing the experiment. You did the experiment. Don't listen to me. You did the experiment, and you did the experiment as best as you could, but maybe you didn't account for the fact that alligators need that visual as well. It could be that you just fucked up the experiment. It could be. All right, it could be that you didn't play the audio right, but you know whether or not you did the experiment. And oftentimes in science, we go to great lengths to make sure that we do the experiment correctly. In any case, it doesn't matter. You cannot know whether it was you or whether there is no pattern. All you know is that you did not find evidence. So in your experiments, you hypothesize that plants grow better in red versus green light, maybe, and you don't find evidence to support that. You don't know whether plants don't like red or green light. You don't know anything. You just know that you didn't find evidence to support your hypothesis. But suppose that they do exhibit splashing behavior when I conduct a playback. And you're like, cool, they did what I expected them to do. In that case, you did find evidence to support your hypothesis. But it still does not mean that your hypothesis is correct. Remember, there is no fact and there is no truth. There's no correct and there's no wrong. All you know is that you found evidence to support your hypothesis. What you actually found is that alligators respond to a stereo. Because of careful and creative experimental design and exhaustive research about alligators, you think that this suggests evidence for your hypothesized mechanism, but you don't know. You do not know whether your mechanism is actually true because there is no truth in statistics. All you know is that you found support for your hypothesis. It is so important that you understand this essential key component of science because so many people out there don't get it. They think that science is the search for truth. It is not. Science cannot find truth. If you want truth, go to a church, go to a synagogue. I don't care where you go to. Put a colander on your head and pray to the flying spaghetti monster, but there is no truth in statistics. All you did in this experiment was reject the null of no pattern. Remember, that's all statistics is about. Congratulations, you did it. And as such, you tentatively accept your hypothesis. That's it. Don't say anything else. Just don't say anything else. Nothing else can be said for any certainty. All you can say is, given what I did and the observations that I took, I tentatively accept my hypothesis. I humbly accept what I hypothesized. Now, switching gears a little bit. How do we make the decision to actually reject the null and subsequently accept the hypothesis? How do we make that decision? At what point, how many observations of alligators splashing do we need before we can actually reject the null hypothesis? In other words, how much of a behavior is necessary to observe before we make a decision about rejecting the null and accepting the hypothesis, the alternative hypothesis? There's an observation that whale vocalizations have become deeper over the past 40 years. This is a real observation. It was found in a paper, published in a paper several years ago, and they wonder why. I hypothesize that marine mammal vocalizations become deeper when density decreases because deeper sounds travel farther. Whales are threatened, and so their density in the ocean has gone down, and as a result, they need to communicate with individuals farther and farther away. And sounds with deeper frequency, lower frequency, travel farther. Note that we're not saying that whale vocalizations haven't become deeper. They absolutely have become deeper. We have the data to show that. The question is just why? And we're suggesting here it's not due to density, that the frequency of vocalization is completely random with respect to density. Given my hypothesis, I predict that increasing the density of whales will increase the pitch of whales' vocalizations. All right, will increase the frequency of whales' vocalizations. How do I do this? I conduct an experiment that manipulates whale density, and I record the pitch of whale vocalizations. How in the hell do I manipulate whale density? I don't know. Details are details are details. Let's say that I somehow managed to airdrop whales in the ocean. All right, that's just hire a bunch of, these look like dolphins, to airdrop whales in the ocean, and I manipulate density in that way. Whatever way. Maybe I do callbacks. I don't know. Let's just, for shits and giggles, say that I manipulate whale density. What I'm going to do is arrange my observations. I'm going to manipulate whale density, and I have one area, which is on top, where there's only one whale in a large area, and then I have an area where there's 10 whales in that same area. And then I measure the frequency of vocalization. The hertz is a measurement of frequency. I measure the hertz of vocalization in both cases amongst whales. And in the situation where there's only one whale in an area, I find that the frequency, that the hertz is somewhere between 5 and like 23, with the bulk of everything occurring between 5 and 15. In the area where there's 10 whales, I find that there are some whales over here that definitely have low vocalizations, but the majority of whales, I see vocalizations up to almost like 35 hertz. Okay, so from this you would say, oh, definitely whales in situations where they're denser, more dense, emit higher pitched frequencies. But what about these whales over here? And maybe what about this whale over here? There's definitely overlap. How much overlap can you have before you say that these two are the same distribution? Well, the average up top is about 12. And the average below is about 23. Are those two averages different? Yes. But we're not too concerned with what the averages are. We are more concerned about the spread of data around those averages. How much overlap is there around the spread of that data? Suppose that there is no pattern and that the null hypothesis is quote unquote true, and the points are really all over the place along these lines. If this were the case, it would be pretty amazing if we just happened to measure the points in yellow. If the null hypothesis were true, we would have a very low probability of measuring only those points in yellow. What actually happened, though, is that we did measure the points in yellow. The lower the probability, the less likely it is that the data is actually all over the place, and the more confident we can be in rejecting the null hypothesis, in rejecting the possibility that the points are all over the place. The farther apart these data are from each other, the less likely that the data was selected from a random distribution, and the more confident we can be in rejecting the null of randomness. When is the probability of rejecting the null small enough that we are comfortable accepting the alternative hypothesis? Now we turn to the infamous p-value, the probability value. That's what p stands for. The p-value, this probability value, measures the probability that observed or more extreme differences would be found if the null hypothesis were true. I know that's a mouthful. We'll get there. Once again, the p-value measures the probability that extreme differences would be found if the null hypothesis were true. There must be less than a 5% chance of recording data that would fail to reject the null. There has to be a very large spread in the data. But it is worth just asking, why 5%? Why did we decide on 5%? This value actually represents a time-tested trade-off between logistical ability to design experiments that we can be confident in and the ability of those experiments to actually detect effects. It is difficult to do science. We spend a lot of time and money. It would be a lot cheaper if we could work with a probability of like 50%. So why don't we go higher than 5%? Well, humans have a psychological tendency to make order out of nothing. We want there to be a pattern. We are looking all the time to find patterns, and we will do so given the opportunity. 5%, oh, for example, when you see this in the clouds, you say, oh, look, it's a bird. It's not a bird, it's a cloud. But you see order. You see patterns in nature. 5% is a conservative p-value which protects us from ourselves. It protects us from finding patterns in nature when there are really no patterns there to begin with.